科会议，学术世界。
Let's start. So first of all, thank you very much to the organizers of the conference for inviting me to give this speech. So it's my pleasure to present today some works that we did last years on control of parallel kinematic manipulators, and especially for industrial applications. So before going further, let me just introduce the context of this study. And this is a typical application, actually, where we can use parallel kinematic manipulators. This is a flight simulator. As you can see here on the top here in the middle of, you have the cabin, and inside you have the pilot. So, and the commands that are controlled by the pilot are connected to the control of the motion of this moving platform holding the cabin of the airplane. And we try to reproduce the dynamics of an airplane. And the down part here, it represents this parallel kinematic manipulator. So we have here 6 legs holding the moving platform, and we have on the ground the fixed platform, and the legs are actuated by motors. And the idea is to reproduce the dynamics of an airplane. So this is a flight simulator, and it's based on the using of a parallel kinematic manipulator. And this is one of the typical applications where we can use this kind of robots. So this is just to introduce the context. And now let me introduce the outline of the presentation of today. Actually, I will start by the context and also the control problem formulation. Then I will show you just an overview about the state of the art concerning the main topic that I'm interested in, the control of these parallel kinematic machines. Then I will focus on the experimental platforms, since all what we developed on the control of those robots has been experimented. So we did real-time experiments, and I will classify those robots in non-redundant PKMs and redundantly actuated PKMs. Then I will shortly emphasize some proposed control solutions, and I will try to motivate the choice of those control solutions before I will introduce the real-time experimental results and the performances. So I will show you the results on different kind of robots. Then I will conclude my presentation by the end. First of all, let's introduce the general context. And let's start with a very basic definition. So what is a parallel kinematic machine or parallel kinematic manipulator? First of all, let's introduce the definition of what we call open kinematic chain robots. So those robots are like this one here, as you can see, and this is the kinematic chain. We have here the base, we have the end effector, and then we have in a serial way, joint body, joint body, joint body, going from the fixed base to the moving platform, or what we call the end effector. And the kinematic chain is open here, and this is what we call serial robots. So the case of parallel kinematic machines or parallel kinematic robots, so the idea is to construct the kinematics in a closed kinematic chain. So here we have the base, we have the moving platform or the end effector, and we have several connections represented the kinematic chains. And here we have a closed kinematics. And here you have an example. So now, what is the difference, or what is the main differences between the serial robots and parallel robots? Let me show you this table. And actually, the table here, we show different properties. We show here the case of serial manipulators and parallel manipulators. And we compare, so the properties between serial and parallel manipulators. For instance, if we look the preferred property in serial manipulators, it's the dexterity. However, for parallel manipulators, the preferred properties is the stiffness. So we have a much better stiff robots if we are in parallel kinematic chains. And then the best application for serial manipulators, it's the big motion. Since we have dexterity, we have a big workspace. And the best application for parallel robots is the precise positioning. So we can reach a much better precise in positioning for the case of parallel robots. And also concerning the workspace, for instance, so the serial manipulators have generally much bigger workspace. However, the parallel manipulators, they have a small workspace. And concerning the modeling of the manipulator, for the serial manipulators, we have a very easy or straightforward to be computed kinematics. However, it's very complicated for the case of parallel manipulators, and the inverse is the case of the inverse kinematics. It's very complicated for the case of serial, and it's very easy and straightforward for parallel manipulators. So this is just to introduce a simple comparison between serial and parallel manipulators. Then a brief historical review. So if we look to the history of development of parallel robots, so the first idea, it goes back to 1931, where this idea to design closed kinematic chains has been proposed by Gwyneth. And it is like a dynamic cinema that this is from his patent, a dynamic cinema here controlled by a parallel mechanism. Then around 1942, Polar, he proposed another mechanism which has also a parallel kinematic structure, and it was designed for painting. 1949, Goff, he proposed this mechanism, which is also a parallel mechanism, and it is used for testing tires. Then after a few years after this invention by Goff, Stewart, he proposed a flight simulator based on parallel kinematic structure, and starting from that date, we call this structure Goff-Stewart platform. Like 20 years later, a guy from EPFL from Switzerland, he designed the first lightweight parallel robot called Delta Robot. And this robot is very well used for food packaging applications, and he designed his mechanism around 1985. Now, where parallel robots are used, a lot of applications and potential applications can be found. So here you have some examples. I introduced the context of this speech by showing a flight simulator at the beginning of my presentation. But we do not have only flight simulators. We have motion simulators in general. So it can be like a boat, it can be a car or tramway, any system that we want to reproduce the motions through a simulator. We have a lot of applications also, and thanks to their very high precision, parallel robots are used in medicine also for several applications. They are used in physics for synchrotrons. We can find other applications for the positioner of telescopes. We have other applications using lightweight parallel robots for food packaging. We have many applications in machining tasks for industry. And we have agricultural applications also where parallel robots are used. And the last one, it's the application concerning the waste sorting where parallel robots also, they are used. So this is just some examples to introduce the context to show you where these kind of robots are actually used nowadays. Let me now introduce the control problem formulation, and they will introduce this problem formulation through 3 industrial applications. Let's start by the first one, and the first application that I want to show you here, it's the case of food packaging. And this is one of the lightweight parallel robots used for food packaging. It's the Adapt Quattro, and this robot has been designed and patented in our lab. One typical application is the food packaging, and the idea here to take objects coming on a belt and put them in a box and repeat this motion. And the challenge is that we want to increase the productivity. So we want to increase the motion of the robot, and we want to reduce the cycle time. So what is a cycle time? The cycle time is illustrated here by the down part of the presentation. So we suppose at the initial that the end effector is somewhere. We go to take an object, then we take the object, we move the object, then put it at the place position, and we go back to the initial position. This is one pick and place cycle. And the idea of reducing the cycle time, if you want to reduce the cycle time, we want to increase the number of picks per minute. So we have to reduce the cycle time. To reduce the cycle time, we have to increase the speed and the acceleration of the motion of the end effector. However, we have a big problem because actually, due to the mechanical vibrations, we may have, at the stop points, at the peak position here and the place position here, we have to stop to take the object, and we have to stop to place the object. And in between, we have to increase the speed and the acceleration. So even if the mechanical structure is rigid, we still have some mechanical vibrations at the stop points. It means at the peak position and the place position. And this is one of the challenges in terms of control of this parallel robot. So we have to control the robot while avoiding this problem of mechanical vibrations that may increase the cycle time instead of reducing the cycle time. If the manipulator is oscillating around the peak position or the place position, we cannot go back to the other position since it's oscillating. So we have to reduce these oscillations while increasing the speed and the acceleration. So this is the first application where parallel robots are mainly used. Let me introduce a second application. And the second application here, it concerns machining. So we know that we have tool machines, numerical machines. We have a lot of solutions. The idea of using parallel robots, it's thanks to their high rigidity. So they are very rigid, so they can be used for positioning a tool, as you can see here. And then the idea is to control the position and orientation of the tool to do a machining task. So actually, we have to control the motion of the tool to do the machining. We have to follow a predefined reference trajectory depending on the shape of the piece that you want to do the machining. And we have another challenge here, because actually the end effector is in contact with the environment, with the piece, and we have to apply a force to do this machining. And this is a very challenging task. So we have to control with precision the position of the tool while managing this contact with the surface of the piece. So this is another application. As you can see also, the control challenge is different from the previous application. The third application that I want to show you actually is the waste sorting. And for waste sorting also, we use parallel robots. As you can see here from this application, we have several parallel robots, lightweight parallel robots. These are delta robots, and they are used for waste sorting. So the idea is that you have a lot of objects coming on a belt here, and these objects we don't know them a priori. So it can be plastic, it can be wood, it can be any other material. And the idea is to do the waste sorting. It means that you put the papers in one box, you put the plastic in another box, and so on and so on. And here the challenge is to do this as fast as possible. And we have to control the parallel robots to recognize first the objects coming on the belt and then put them in the right box. So these are the three main applications on which I want to introduce the context of the control problem formulation. Now let me focus on this control problem formulation. And before that, let me here summarize the different topics in terms of research around parallel robots. So if you are interested in parallel robot, we have several research topics. One of them is the mechanism design or mechanical design of the robot itself. to study the stiffness, to study the architecture, the design, the optimization of the design itself. For instance, this is one very interesting topic. We have another topic here. It concerns the modeling itself. So when we are interested in parallel robots, we have to compute the dynamics. For instance, we have to compute a dynamic model. And this is also a very challenging due to the closed kinematic chain and other uncertainties that we may have. And also we have the problem of computing of the kinematics. So the modeling aspect is a very interesting topic also around parallel robots. We have a third research topic. It concerns the motion planning. So if we want to do a task, we need to generate some predefined trajectories, and we want to control the robot to follow those trajectories. So we have for the motion planning, trajectory generation, and we have also the singularity study. And the last research topic that I'm interested in here, it's the control. And if we are interested in controlling of a parallel robot, we have several solutions that we may propose. We have the vision-based control, and we'll have also the sensor feedback-based control. If we are interested in control of parallel robots, we have firstly to know that the dynamics of the robot itself, it's highly nonlinear and it's very complex. It's very complex because it's like the dynamics of a serial manipulator. And to these dynamics, we have to add the constraints of closing the chain because we have closed kinematic chains. And we have to add those constraints while we compute the dynamic model. Then this dynamic model, so it has a highly nonlinear aspect, and we have also a coupling between the different degrees of freedom. And finally, if we rework the dynamic model of the robot, it can be represented like the one of the serial manipulators in this way, while including the constraints of the closing the kinematic chains. When we compute the dynamic model, we have also the problem of uncertainties because we cannot know specifically and with precision all the parameters and all the terms of the dynamic model. So we have several uncertainties that may be considered in the dynamics. Those uncertainties, they are due to the geometric errors, for instance, or parameters variations. Sometimes during the motion, some of the dynamic parameters, they may vary with time. And this variation, it creates these time varying uncertainties. And also we have some non-man-modeled phenomena, and we have also the operating environment. Sometimes the manipulator is in contact with the environment, so we have to deal with this interaction between the manipulator and the environment. Then we have also another issue. Actually, when we design a parallel manipulator, sometimes we have a fully actuated manipulator. It means that we have certain number of degrees of freedom and a certain control inputs, and the number of control inputs, it's equal to the degrees of freedom. However, sometimes we have what we call the actuation redundancy. It means that we have more control inputs or more actuators than the degrees of freedom. And this problem of underactuation may create what we call the internal efforts. And these internal efforts may damage the mechanical structure if we don't care about them. And this is just an illustration of this actuation redundancy. Here on the left, you have a non-redundant manipulator. So we have 1, 2, and 3 actuators here. And we have 3 degrees of freedom, 2 translations and 1 rotation. And this is a fully actuated manipulator. However, on the right part here, we have a redundantly actuated manipulator because actually here in the middle, we have the moving platform. It can do 3 motions, so 2 translations, X and Y, and the rotation along the Z axis. However, we have 4 inputs or 4 motors, 1, 2, 3, and 4. So we have more actuators and degrees of freedom. So when we design control schemes, we have to make the specific attention, careful attention to this actuation redundancy, and we have to manage this in the control design aspect. And the last point or the last challenge when we deal with control of parallel robots is the problem of measurement, because actually and mainly we can measure the joints, we can measure the joints motions of the manipulator, but it's very difficult, or most of the time you cannot measure the motion of the platform itself. So we have a measurement in the joint space, and sometimes we design controllers in the operational space, and we do not have the right measurements in this operational space. So we have to move from the joint space to the operational space by using a model to compute the equivalent position, for instance, in the operational space, and we control the robot in this space. And this is also one challenge in terms of controls, because we cannot measure all the states of the system in both joint and operational space. Now, our idea is to work on control for those robots, and the idea is to improve the dynamic performance of parallel robots. And we want to improve this dynamic performance in terms of motion speed. We want to increase highly the speed and the acceleration. So we did some control solutions to reach up to 100 G of maximum acceleration. Then we did another work where we were interested mostly in accuracy. We want to improve the accuracy of the parallel robot and doing a slow motion, not a very high speed motion. So we were interested by the motion speed first, then we were interested in accuracy second, and then the third objective was to take into account both situations or both aspects. So we want to design a high speed and accurate parallel robot, and this is very challenging, because if you increase the speed and the acceleration, you may degrade the accuracy. And if you go with a slow motion, you can reach a very high or very good accuracy. But if you want to do both of them at the same time, this is a problem. That is a challenging control problem. And also we want to improve or to enhance the robustness of the control of those robots. It means that if we change one of the situation of the operational space, for instance, we change the payload of the robot and so on, we want that our developed controller keep the same performances while this modification or uncertainties or external disturbances coming from this environment. And this is what we call the robustness. So we want to design robust controllers for those robots. Actually, in the terms of methodologies, we proposed different control solutions. Some of them, they are adaptive nonlinear control. We designed also nonlinear robust control, nonlinear model predictive control, and we designed some specific controllers to compensate for the errors coming from the actuators dynamics, from friction, and so on. And also, for all the proposed control solutions, we were interested in the proof, in the theoretical proof of the stability analysis of the resulting closed-loop system. And this is very interesting to ensure that the control scheme will be stable when we close the loop with the robot. And in terms of validation, we proposed all the proposed controllers has been tested in real situations to control the motion of some robots. So we tested in various operating conditions, including the nominal case where we do not have any external disturbances. Then we consider the case of high-speed motions. We considered also the case of additional payloads. So we add the payload and we check the robustness of the proposed controller. And we tested also the robustness with respect to a variation of the motion speed or the reference trajectories. Let me now, before showing you our proposed control solutions, introduce the state-of-the-art on control of PKMs. Actually, if we look to the state-of-the-art on control of serial robots, we have a lot of papers that have been proposed, and we have much less controllers proposed for parallel robots. But the proposed controllers for parallel machines, they cover a lot of kind of controllers. And actually here I introduced just this classification to explain you the existing controllers and how they can be classified. First of all, we can distinguish two subclasses of the proposed controllers. So the first subclass, it's called non-model-based controllers. And the second class, it's the class of model-based controllers. For the case on non-model-based controllers, those controllers, they do not rely on the dynamic model. So you design the controller, you don't need to know perfectly the dynamic model of the robot. And the design of the controller itself do not need to know this dynamic model. And for the family of non-model-based controllers, we can also classify them into subfamilies concerning the non-adaptive controllers and adaptive controllers. For the case of non-model-based, non-adaptive controllers, you have the famous PID control, we have nonlinear PID control, we have rise feedback control, nonlinear rise feedback control, and so on. All those controllers, they are non-adaptive and they are also non-model-based. Then we have the subclass of non-model-based adaptive controllers. And the idea here is to make the previous controllers adaptive. We have the case of L1 adaptive control. We have other controllers, ADRC, proposed in the literature. Then if we look to the case of the second family or the second class, model-based controllers, here you need to know the dynamic model because the design of the controller itself, it's based on knowledge of this dynamic model, and the design itself, you need to know these terms. And we can classify them also in non-adaptive controllers and adaptive controllers. And the non-adaptive controllers, we have, for instance, the PD plus controller. It's an augmented PD controller. We have the dual space feed-forward controller, computed torque. Computed torque, it's a non-adaptive model-based controller. Sliding mode control, and so on. And we have the case on model-based controller, adaptive controllers. And for those controllers, we need the dynamic model. We suppose that we don't know perfectly all the terms of the dynamic model. We do an online estimation of some parameters of the system, and they are used in the control design. And we have, for instance, the PD with an adaptive feed-forward, the dual space adaptive controller, and the DKAL feedback controller. Now, our experimental platforms. Actually, we have a lot of robots on which we designed our controllers and we tested them. And here I try to classify them in non-redundant PKMs and redundantly actuated. So the first prototype is called Part 2, and it's represented by this CAD view, and the real robot is represented here. So we have a spatial mechanical design here. You can see the closed kinematic chains. We have but it has only two actuators, the blue parts here on the picture, and the two other kinematic chains, they are rigid and they are used just to keep the motion in this plane. And this robot has been designed, it has just 2 degrees of freedom, 2 actuators, and it has been designed for a pick and place applications. I will show you some videos to understand how it works. Then we have the case of R4. And R4, it has also a structure which not very difficult, very different from the previous one. However, here we have 4 motors. So for each kinematic chain, we have a motor, as you can see here. And this robot has 4 motors and 3 degrees of freedom of motion of the moving platform here. So 4 motor versus 3 degrees of freedom. So the robot is redundantly actuated, and the actuation redundancy is of degree 1. The next one, it's Veloz. It's like the previous one, like the R4. However, here, and the idea is to introduce a rotation around the Z-axis of the moving platform. And this has been done thanks to this traveling plate, as you can see here, designed based on 2 parts, and here a screw in the middle. And if you move one part with respect to the other one, you create a rotation along the Z-axis. So we have 4 motors here, and here we have XYZ 3 degrees of freedom, and the created rotation, it's 1 degree of freedom more that we have to be considered. And we have, so 4 motors and 4 degrees of freedom, 3 translations and 1 rotation, and the robot is non-redundant. The GLV robot, the next one is called GLV, and it has 4 actuators, as you can see here. the arms and forearms and the traveling plate, it's in the middle here. And this robot has been designed for some specific industrial applications, like, for instance, laser cutting. So you can fix the laser head here, and you control its position and orientation to do the laser cutting of some pieces. So it has 4 motors, and here 3 degrees of freedom, and it is redundantly actuated. The next one is the Delta robot, and this is the classical one, designed by Professor Clavel at EPFL. So we did a cooperation in this work just to compare our proposed controllers on this experimental platform and to check the robustness of the controllers. The next one is called T3KR, and this robot has been also designed in our lab, and it has almost the same structure than the previous robots. However, there is a specific difference here, which is the traveling plate. So the traveling plate of the robot, it has been designed in a compliant way. So it includes a compliance inside this traveling plate. And here we have 4 motors and here 3 degrees of freedom. So the robot is redundantly actuated. And the mechanical design here was done to take care of this redundancy, actuation redundancy. So if there is some internal efforts, thanks to this compliance in the traveling plate, we can absorb these internal efforts. And this robot has been designed for pick and place applications. So we did some tests for waste sorting. And the 2 last robots, so they are designed for another industrial application. It's the case of machining. So the first one, it's Arrow. And Arrow, it's different from all the previous robots in its actuation, because actually here the actuation, it's based on using of 6 motors, and all those 6 motors, they are linear motors, not rotating motors. So 6 motors, we have here the parallel platform, and the traveling plate or the moving platform, it's here. And here the tool will be fixed, and it includes a motor that rotates the tool, and we have to control the position and orientation of this moving platform to do machining tasks. And the last one, Spider 4. And Spider 4, it has a specific architecture, because actually it includes a first part, which is a parallel kinematics. And here the end effector, since for machining we need 5 degrees of freedom, so actually we have 3 degrees of freedom coming from this parallel structure, but we added here 2 serial, we have two motors in a serial way. So it's like a hybrid architecture, a parallel followed by a serial one. And the serial one, it has 2 motors to control the orientation of the machining tool that you can see here. And also to reach the needed number of degrees of freedom for doing machining, which is 5 degrees of freedom. And also I have to remark for the previous one, for Arrow, here we have 4 degrees of freedom to do the machining. We have X, Y, Z, and the orientation along the Z axis. However, as I said, we need 5 degrees of freedom to do the machining. So the 5th degree of freedom is coming from this table. It's a turntable where we will fix the piece to be machined here, and we can control its orientation. So this is the 2 last robots. And now let me just give you an overview about the proposed control solutions. So we work a lot on different control solutions that we implemented and tested for the control of parallel robots. We proposed geospace feed-forward control, geospace adaptive feed-forward control, direct compensation adaptive control, adaptive race control, and so on, and also terminal sliding mode control. And all of them, they have been experimented on different kind of prototypes that you can see here on this slide. And I have just to mention something which is very important here. And as you can see from the control solutions, I emphasized with the red color here a word, which is adaptive, 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 adaptive. And here there is an idea behind using adaptive control. When we do, the application of parallel robots, mainly, as I said at the beginning of my presentation, there will be strong uncertainties. We cannot know all the parameters of the robot and its environment with precision. So we have to pay attention, and we designed adaptive controllers to take care about these uncertainties and to get the good performances while the dynamic parameters or some operating conditions are changing. So this is the proposed control solutions. Let me now show you some videos about the real-time experiments. So the first application here, it's for a pick and place in 2D, as you can see here. This is the first robot part 2. And here we did a pick and place motion with different maximum accelerations. Here, a 50 G of maximum acceleration with a cycle time of 0.21 seconds. And this is a motion in the plane XY. And as I told you, we try to increase at maximum the speed and the acceleration to reach a 50 G of maximum acceleration. G is the gravity, and 50 G, it means like 500 meters per second square. A second application of the same robot part 2 is represented by this video. It's playing with a ball first, 3 balls. First, it starts with just 1 ball, and then we release the second ball, and we check if the robot is able to pick the ball before the second one is arriving, and then playing with 3 balls. So it means the robot has to accelerate while doing this motion. So in the papers, you can see all the details of the proposed controllers that you can see on the videos. Then on the R4 manipulator, so we did also different tests, and we developed here a dual space adaptive controller, and you will see here 2 scenarios with 30 G of maximum acceleration and 40 G. And you see clearly the difference between 30 and 40 G, because actually even with just seeing the videos, we can see that 40 G, it has much better speed motion than the case of the 30 G. Here we did the case with some uncertainties. We attach here payload on the traveling plate, and we repeat the same 3D pick and place motion to track the reference trajectories. Also the same here in the paper, you can find all the details of the proposed controller. Then we tested the same controller for 2 other scenarios. First one, it's a spiral motion like that. So it's a rotation while we increasing the amplitude, and we increase also the speed and the acceleration. And the last one is the scenario of 100 G, and it was a very, very high maximum acceleration. So the idea was to do a vertical motion. We start at the middle, then we try to increase the speed and the acceleration and also the amplitude until we reach a maximum acceleration of 100 G, which is here in the middle. And this is the measurement of the acceleration. So we placed here an accelerometer, and we measure in real time the linear acceleration, and it was effectively 100 G. And this was a world record of a maximum acceleration of robot, and has been reached around 2015, as you can see in this publication. Another application actually is the enhanced direct compensation adaptive law. And this is the test that has been done on GLV robot. As you can see, the moving platform here in the middle, and we try to control the 4 motors to follow a predefined reference trajectory of the moving platform here in the middle. And we did different tests and different situations, and we try to test also, as I told you, the robustness of the controller. So we added here a payload that we have fixed on the moving platform, and then we try to repeat the same motion, and we compare the case of added mass with the nominal case, and to check if the controller is robust enough towards this added uncertainty. The next application, we compare the classical rise, it's the robust integral sign of the error, with an adaptive version that we developed, and we tested on the EPFL prototype Delta robot here. We did also 2 scenarios. So the first one is the nominal, and the second one, we added here a payload, and we repeat the same scenario for the tracking of these 3D pick and place trajectories, as you can see here. And you can see the performance of the controller in the research paper. Then we worked on the L1 adaptive control, and we proposed an extension of the L1 adaptive control by adding first a feed forward based on the dynamic model to improve the tracking performance of the controller. And here, as you can see, the motion of the traveling plate. Then we augmented the L1 adaptive controller with feed forward, and we compare the results, and we show that the proposed controller has a better performance than the original L1 adaptive controller. Then for the waste sorting, we proposed to work on the optimization of the reference trajectories, and we compared a new solution called pick and throw, because actually for waste sorting, you have seen on the illustrative video a pick and place solution. So the pick and place, it means that the traveling plate or the moving platform stay inside the workspace of the robot, which is small, and we have to take the object from the pick position, place it here. In our case, we did the pick and throw. It means that we throw the object to go inside the box. And we repeat this motion, and we compare both solutions for the pick and place and pick and throw. And we try to show that for the pick and throw, we can have more picks per minute. And here we compare the proposed one with another existing pick and throw solution for the literature. And here the third experimental scenario, where we can see that we have more picks per minute compared to the existing pick and throw solution. And we can throw the objects outside of the workspace. And as you can see, it's faster. Existing than pick and throw, and compared with the existing one. And we did the different tests with low speed motion here and high speed motion, as you can see, and the existing one and the proposed one, as you can see. And you also the same, you can find more details in the paper. Then we did another application for machining. Here we designed the PID augmented with a feed forward and with an anti-wind up. And here is the machining task that we did. So we predefined some reference trajectories. We control the moving platform of this arrow robot, and we try to follow these reference trajectories to do the machining. As you can see, the motion of the linear molders here, this is the platter platform, this is the machining tool, and inside we have the molder. The tool is here activated by this molder. And this is, as I explained, also the turntable, because the moving platform, it has 4 degrees of freedom, and here the turntable, it has 1 degree of freedom, and then you can see also how we can control the orientation of the piece by rotating this turntable. And we have to follow the reference trajectories to get the piece that you want to do the machining. And also you can see more details about the proposed control solution here in this paper. So this is also for machining, and let me show you another scenario for machining. It's on Spider fork. And as you can see here, we compare the RISE controller versus the RISE augmented with feed forward, and also an adaptive version. And here we put 2 cameras. We can see here the moving platform. The tool is here. And here in front of the tool, we have the piece, as you can see. And you can find all the details of the adaptive proposed RISE controller in this research paper. And here, as you can see, an illustration of the task that you want to do as machining. We worked also on for the applications of flight simulator on hexapods, and the hexapods, they have it's the steward platform. It has like 6 legs, as you can see. The fixed base here, the moving platform is here. We designed these reference trajectories, and we try to control the motion of the moving platform. And we try also to evaluate the performance of the controller in terms of tracking errors. And as you can see here, the tracking errors, these kind of robots, they have a very, very high precision. So the tracking error here is less than 30 micrometer. And here, the down picture here, it represents the evolution of the torques applied to the 6 molders of the robot. I will show you the case of here of uncertainties. We added here a payload that has not been considered in the dynamic model initially, and we have in real time an estimation of this payload. As you can see here, estimation, it goes to the right value, and also we have the tracking of the predefined trajectories. And here we have also an estimation of the center of mass, because actually we can put the payload in a position where it's not in the center. And the last scenario, and here we have another scenario where we move this payload to move the center of mass. And as you can see, the estimation is working well. And the last scenario, we try to increase the speed of motion and to show the robustness of the controller with respect to the change in the motion speed. A last video here, it shows the control using nonlinear model predictive control, and the application here is a cable-driven parallel robot. So as I explained at the beginning, one of the issues of parallel robots is the small workspace. To have a wide workspace, a big workspace, we can design cable-driven parallel robots. So the traveling plate or moving platform is in the middle here, and it's attached with motors with the cables to the motors, and then we control the motors to pull the cables and to move the moving platform in the space. And you can have a very, very large workspace here. One very challenging problem regarding the control of cable-driven parallel robots is, in terms of control, it's the saturation of the control inputs. I explained, because we are using here cables, and the cables, they are flexible. So we can just pull cables, we cannot push. And we have to keep a certain tension in the cables all the time. And this is a very hard constraint that we need to consider. And this is why we proposed a nonlinear model predictive controller, where we can include the saturation of the actuators inside. Here we compare the two cases, like a PID controller and a linear model predictive controller, to show that we can manage all the situations. So let me now conclude my presentation. So the topic of today that I shared with you is the problem of control of parakinematic manipulators for very high acceleration and precision applications. So we distinguished two case studies, non-redundant robots and the redundantly actuated robots. And we have only measurements in the joint space. We were faced to a lot of challenges, like we have to deal with the highly nonlinear dynamics, the operation conditions that may change, also with the actuation redundancy, the real-time constraints, the constraints like on the cable robots, for instance, and also the problem of mechanical vibration. So we have to deal with all those challenges and problems. We propose different control solutions, nonlinear robust controllers and adaptive controllers, and also model predictive control. And we did different validations in numerical simulations that I didn't present it here. I focused on real-time experiments, and we did maximum acceleration for non-redundant case with a 50G and 100G of maximum accelerations for the case of redundantly actuated. And we did also other industrial applications like machining, and also other applications for cable-driven parallel robots. So with this last slide, I finish my presentation, and I give you just a few links here if you want to see more videos. I have a YouTube channel here. You can see more videos on my research activities. You can see also research papers. And with this last slide, I finish my presentation, and I thank you very much for your attention.